a graph is a pair, B comma E. So it's a pair of sets where B is a set, okay? And for the purposes of this course, whenever, V is, this set V is almost always going to be a finite set. And E is a collection of subsets of V of cardinality 2, okay? And, okay, the elements of V are called vertices. So that's where the V comes from. So vertices is like plural. So plural is vertices, plural. And singular, if you talk about one element of V, singular, you say vertex. Although I remember when I first learned about graphs, and it's pretty common to like kind of mix these things up and start saying vertexes or like a single vertex, like, instead of vertices. But yeah, try to keep it so straight that if you talk about one element of V, it's called a vertex. If you talk about, multiple elements of V, they're called vertices. And the elements of E are called edges. And I guess clearly a single form is just edge. Okay, this is a kind of an abstract, technical definition of a graph. But yeah, okay, so let me just give you an example. So, but yeah, basically, like this is a technical definition, right? A graph is a bunch of points called vertices and pairs of, so edges are pairs of vertices. But there's a better way to kind of illustrate this. But anyway, so let me look at this example. So V is the set A, B, C, D, E, and E is the set. So remember, E is a collection of subsets of size 2. So it's AB, AC, AD, CE, and CD. So technically, if I let G be, V, the pair VE, then G is a graph. Okay, so this is just one example. But yeah, this is almost never, like just writing the notation is almost never the best way to think about graphs, right? The best way to think about graphs is kind of with a picture. So how would we make this graph into a picture? So what you do is you take the vertices, A, B, C, D, and E, and you represent the vertices as points. So I've got a point A here, B, C, D, and E. And the way you represent the edges is as lines which join pairs of vertices. So the first edge here is AB, right? And we can represent this by a line that joins A to B. So this is like a representation of the edge AB. So I get an edge between A and C because of the second edge. I got A and D, I've got C and E, and I've got C and D. Okay. And okay, so this is the way we usually think about graphs, is in terms of these kind of pictures, right? So when you hear the word graph, what you should really think about is like some sort of connect the dots thing, where you have these dots, which are the vertices, and you connect pairs of them with lines. And you can, yeah, and basically a graph is sort of a representation of a network in some sense, right? You could think of the points as being, the vertices as being cities or something, for example. And you can think of like the edges as being roads that join the cities, right? That's one particular example, but there's a lot of different things that can be represented by graphs. So is this all clear so far? Okay. So yeah, here's another notational thing. So I'm claiming, okay, I personally don't like writing squiggly brackets. Squiggly brackets, I mean like, yeah, these things, these, these kinds of things. And so, I mean, because nobody really likes writing squiggly brackets, so formally an edge in a graph is a subset of size 2 of the vertices, but we usually don't write it as like, if the edge is UV, we usually don't write, set U comma V. It's usually good enough to just write like UV, kind of concatenated. So for example, if I take V, so if I define a graph, I can define a graph this way, taking V to be the set X, Y, Z, W5, and I let E be the set X, Y, X, Z, Y, W, X5, WZ, and 5W. So formally, this is the same thing as like, if I, X, Y is the same thing as if I had the set X comma Y, right? It's just a different kind of notation. And that would give me this graph below. I hope anyway. I hope I haven't messed it up. but I think that's the graph that you get, right? You have x is joined to y, x is joined to z, y is joined to w, and so on. So if you prefer, when you talk about an edge between two vertices, let's say u and v, you can just write uv instead of the set containing u and v. Yeah, so another kind of notational thing, I guess, is that, the way I've defined graphs is that you should define v equals something, e equals something, and write g equals the pair ve. Often it's more convenient to just define a graph g and then refer to the vertex set of g. So just to, I'm not sure if this is clear or not, but if g is a graph, that's a good question. Why do we use brackets to combine v and e as a tuple rather than another set, rather than writing v e like this? I think formally there's no good reason, because I guess, well, there could be confusion. I suppose there could be, in theory, there could be some confusion or something. It's just maybe it's better to just have an order so that the vertices come first, the edges come second, so then there's no ambiguity, although probably there wouldn't be any ambiguity anyway. But I guess that's just the standard way of doing it, is to write it as a tuple VE rather than a subset or a set of two sets. So yeah, vertices come first, edges come second, but there's not a super good reason for that. Okay, so if I have a graph, so we often, so you may define a graph without specifying what is V, what is E. And when you do that, then we still want to be able to say what is the vertex set of G and what is the edge set of G. And the notation we use for that is V of G and E of G. Okay, so for example, let's say I just say, sometimes you can just define a graph in terms of a picture, right? If I just say, let G be the graph like this, so let G, sorry, I'm writing kind of in the middle of the slide, let G be the graph like this, right? And then I can say, okay, let V be an element of V of G, okay? And it should be clear from the picture and from the way I've defined G that V of G is ABC, right? And you don't have to necessarily define graphs in terms of a picture either. You can define them, in various different ways. And then when you do that, V of G is the vertex set and E of G is the edge set of G, if that makes sense. So again, this is going to be pretty heavy on definitions, this lecture, but we're going to use all of these things later, so it's important to get it straight. So are there any questions about anything? That was a good question about vertex set and edge set, but okay. Okay, another definition. There's going to be millions of them. So suppose that G is a graph, and I've got two vertices in G called U and V, such that UV is in the edge set. So if you think of the picture, what this means is that, so U and V are vertices, they're points, and there's an edge going from U to V. Maybe I'll just draw it. So I've got U, I've got V, and there's an edge here. We say that, so if there's an edge between U and V, then we say that U and V are adjacent, okay? So if I ever say, take a pair of adjacent vertices or something, that means take a pair of vertices with an edge between them, okay? Now there's a similar kind of definition in terms of interactions between vertices and edges. So if E is an edge, so notice I'm writing just one letter to kind of refer to the edge. I'm just saying, E is the edge between S and T. So that just means that E is equal to ST, So if E is the edge between S and T, we say that E is incident to S and that E is incident to T. Okay, so the vertices S and T would be adjacent. The edge S would be incident, the edge E would be incident to the vertex S. Okay, again, just some definitions. So in this picture here, this picture of X, Y, and Z, E is incident to Y. That's true because it's an edge that contains Y. And X and Y are adjacent. That's true because, X and Y are adjacent because there's an edge between them. Y and Z are not adjacent because there's no edge between them. And now another way of saying the same thing as adjacent, it's sometimes kind of convenient to say that like adjacent vertices are neighbors. So if I say pick a vertex V and pick a neighbor of V, that means pick a vertex which is adjacent to V. Okay, so adjacent vertices are called neighbors, or you can say that they're adjacent to each other, or you can say that the edge is in E of G. Okay, it seems like a lot of ways to say the same thing, but all of these things are kind of convenient in different scenarios. But is it clear what I'm saying here? Apologies again for so many definitions. Okay, another thing. So if I've got a vertex V in a graph G, the degree of V is the number of vertices that V is adjacent to. And we denote that by like deg G of V, okay? Equivalently, it's this, equivalently, it's the degree of so deg, so yeah, the degree is denoted by deg subscript G of V. So that's just to make sure we are aware of which graph we're talking about. And equivalently, it is the number of edges incident to V, right? So in this graph here, the degree of V is 4, because if you look at V and you count up the edges coming out of it, 1, 2, 3, 4, that's the degree. And this is like kind of referring to something I said earlier, that, in your assignments and things like that, like I'm totally happy with you to define a graph by specifying the vertex set, like writing V equals X, Y, Z, W, and then specifying the edge set, E equals X, Y, Y, W, Z, Y, and saying, okay, let G be, let G be VE. Like that's a perfectly acceptable way of defining a graph. But in a lot of cases, like it's more convenient for you and for me and for the marker and everybody if you were to define a graph just using a picture, right? You don't have to. So any kind of correct way of defining a graph is perfectly valid. But yeah, you can also just say, let G be the graph and then draw a picture, right? And you can see that this is a little bit more efficient than doing it in the formal way, because what would I have to write here? I'd have to write let V equal RST U V W X Y. Okay, that's not so bad. But then you have to write let E equal RS, RU, SU, UV, VT, ST, blah, blah, blah. And like, first of all, it's pretty easy for you to just miss one of the edges like that you wanted to be there and kind of make a mistake that way. And also it's hard for the marker to visualize like what is this person talking about in terms of the graph. But like I said, yeah, it's perfectly okay to do that. For example, if you are typing your assignment, you might find that easier to just write the stuff rather than inserting a picture. But I would probably encourage you to draw pictures if you can, but it's not mandatory, okay? Any questions about anything so far in terms of definitions and stuff? So I wanted to do this as a poll. Okay, so I've had 20 people respond to this, the poll that I've got here. So maybe I will end this in a second. So if you want to respond to this poll that I've got going and you haven't yet, then feel free to. So I'm just going to kind of take a snapshot of the results so that I can use them later. I don't know if there's an easier way to save polls afterwards than taking an actual picture of the screen, but okay. So I'm going to end this poll about the course. Doesn't seem like anyone else is answering it. And I will, yeah, okay. So I'll launch this poll about this graph. So this is just testing you on these questions. Which of the following statements are true about this graph? So the options are, so like there might be many things that are true about the graph. So pick more than one if you want. So is 1 adjacent to 6? Is X 9 in E of G? And so on. Or if there's any questions about any of these things on, please let me know. But are you able to see the poll right now? Oh, okay, we've got some answers coming in. I better check whether I know which ones of these are true. Okay. Okay, so it seems like, so we'll start kind of discussing this, but keep answering if you want. So it seems we're getting consensus on the first one, and it's the correct consensus. So 1 is adjacent to 6. That's true because 1 and 6 are vertices, and there's an edge between them. So 1 is adjacent to 6. The first thing is true. X9 is in E of G, X and 9. And that's true. So yeah, the statement was saying like X9 is in E of G, G is this graph. And that's the same thing as saying that X is adjacent to 9. Hopefully this G here doesn't look too much like a 9. Maybe that confused people. But yeah, X is adjacent to the vertex 9. So the second one is also true. F is incident to X. Yeah, that's true. So F is an edge here, right? And it is, in fact, incident to X. So that's correct. 3 is in the vertex set of G. Well, yeah, if you just go through and look, hopefully it's clear like what I was labeling as vertices. But yeah, so 3 is not in the vertex set of G. That there's a consensus there as well. So that's good. It's correct to say that 3 is not in V of G. G equals XW, that's true, right? If I look at G as the X, so G is the edge between X and W, that's true. 9 is adjacent to W, that is false, right? Because look at, so maybe there might have been a bit of confusion again about this G looking like a 9, I'm not sure. But even if I said G was adjacent to W, that would also be false. But if I look at 9, 9 is here, W is here, they're both vertices. There's no edge going between them. So W9 is not in E of G, so they're not adjacent. I'm not sure if there was confusion about this G looking like a 9 or not, but also it would be the case that G is not adjacent to W, because so it is incident to W, but it's an edge, so it can't be adjacent to something, right? Vertices are adjacent, edges are incident to vertices. W2 is not in the edge set is the next question, which is correct. The degree of X is at most 5, or less than 5 is correct. The degree is 3. And nobody said that doing polls is a waste of time, which I'm glad about because I've been doing quite a few of these. Yeah, I think it's useful for people to kind of engage with the topic. So, okay, so we had a mixture of results on everything except for a few of them, but I think the majority got all of these correct. Okay, so I really apologize for having so many definitions, but we kind of do need them. Okay, another definition. So let G be a graph. A subgraph of G is sort of maybe what you would think. It's like a subgraph of G is a graph which is like contained inside of G, like it's a smaller graph that's inside of G. So a subgraph of G formally is a graph H, such that the vertex set of H is contained in the vertex set of G, and the edge set of H is contained in the edge set of G. And the notation we're going to use is that we write G as a subgraph. So we use subset notation. So if I write H subset of G, so when I say the word subset, I mean the subset notation. What I mean is that H is a subgraph of G, okay? By which I mean that both of these things are true. The vertex set of H is contained in the vertex set of G, edge set is contained in the edge set. So we have a question. Can a subgraph have edges that connect vertices that aren't in H? That's actually a good question. Maybe I kind of, technically there isn't anything missing in my definition, but it's a bit subtle. But that's a good question. So here, like I've just said that the vertices of H have to be contained in the vertices of G, and the edges have to be contained in the edges. In theory, that looks like it could be the case where I, maybe I'll draw a picture of this, or maybe I'll come back to this in a second. But let's put a pin in that for a second. I'll just go through this example and then I'll address that question. So just to to go through this example, so suppose I let G be the graph that looks like this. So it's the vertices are A, B, C, D, E, F, and the edges are as in the picture. And then I let H be the graph A, B, quite similar. So it's except the vertex F is missing, and there's various edges missing. And is it the case that H is a subset of or a subgraph of G? Here I would say yes, because if you take a look, like all of these vertices are vertices of G, and all of the edges are present. All of the edges of H are present in G. But for H prime, I would say no, because is that correct? So it does have all the right vertices, like A, B, C, D, and F are all vertices of G, but it's got this edge like from D to F, which kind of breaks things. So so that makes H prime not a subgraph, right? Okay, now let me say something about this question in the chat. It's a very subtle, good point. So in theory, let's see. In theory, like, I mean, suppose G is this graph. Like, I'm just going to pick like, so G is this graph. In theory, I could say, okay, what if I take H to be the graph where I take A and B as my vertex set, and I take the edge set to be AB and AC. Like, so like it seems like it almost satisfies the definition because the vertex set is contained in the vertex set, right? And the edge set, like, so that's equal to V of G, right? And this is V of H. And the edge set is contained in the edge set of, so the edge set of H is contained in the edge set of G. C, BC, which is the edge set of G, edge set of H. Here's the reason why this isn't a subgraph. So I claim that H isn't a subgraph of G, even though it looks like it is. Here's the problem. It's not a graph. So H is not a graph because AC is not, like if I take, let's say I write it in the set notation, AC is not a subset of the vertex set of H. So to answer the question in the chat, can a subgraph have edges that connect vertices that aren't in H? The answer is no. Not so much because of the subgraph condition, but because of the condition that H has to be a graph. So I hope that wasn't too confusing, but does that answer the question? Okay, cool. Yeah. Okay, we say that two graphs G and H are isomorphic. So another definition, if, so there is a function, so let's say, so I've got graphs G and H, they are isomorphic if there's a function V of G, so F, which maps the vertices of G to the vertices of H, such that F is a bijection. Do we remember what bijection means? Probably saw this in 122. So a function is a bijection if it's one-to-one and onto, right? So, or in other words, if it's injective and surjective, okay? And it has the property that UV is an edge of G if and only if F of V is an edge of G, sorry, an edge of H. Okay, so basically the function F kind of associates each vertex of G to a vertex of H. And well, and it does so in a way that like all of the edges get preserved and also all of the non-edges get preserved, okay? So a bit of notation. So to say that G and H are isomorphic, we write, well, this funny equal sign. So we write G, like, so this symbol here will just mean that G is isomorphic to H. Something else I should add is that the function F is, so we call it an isomorphism. So we call, can people see this at the bottom? Maybe I'll give a little bit more space. Call F an isomorphism. I sort of am guessing that maybe not everyone will like this definition in the sense that it's a little bit kind of technical looking. It doesn't really, yeah, if you have to do some thinking to figure out what this is actually talking about. But for all intents and purposes, like the way you should think of two graphs as being isomorphic is like two graphs are isomorphic if they're basically the same graph. Now, they're not formally the same graph because they might have, their vertices might have like different names, like the vertex set might be, the vertex set of G and H might be a different set. So formally, isomorphic graphs might be different graphs, but to say that two graphs are isomorphic is kind of to say that, up to just changing the names of the vertices, these graphs are the same thing, if that makes sense. So yeah, maybe I'll even write that here, that like it means that, I don't really have anywhere to write it, but I'll write it here. So isomorphic graphs kind of means they're the same graph up to changing names of vertices. Vertices. Okay, that's tiny, but okay. And this is exactly what I just said. So, okay, here's an example. So these graphs I claim are actually isomorphic. They don't look quite the same because I've drawn them differently, right? But if you just think of the adjacencies between the vertices, you can see that they're kind of the same, right? So, for example, if I look at the vertex t, imagine, so I'm going to kind of color code things. So I take a function that maps t to alpha. I'm going to map, I should be a little bit careful. Okay, I'm going to map u to beta, right? If I map v to gamma, like you can see that, so far, like if I look at a or alpha and beta, they have the same, like they have an edge between them, and so does t and u, right? So it's looking good. If you checked all of the different things, it would look good. Delta is pretty much the same as y, right? And then I map x to eta. If you don't know your Greek letters, this might be confusing. Apologies for that. W goes to epsilon, and Z goes to tau. Okay, so formally, like if I had to, like sometimes you may be asked, for example, to give an explicit isomorphism between two graphs. If I did that, what I would write is that like f of t is alpha, f of u is beta, and I would just write this whole list, and then that would be an isomorphism. Okay, is this clear? So is it clear that these are practically the same graph, except that they have different names on the vertices? And that's what isomorphism means. Okay. Here's a few things. So the way to show that two graphs are isomorphic, or generally the best way to do it, or the simplest way to do it, is to just find an isomorphism. Sometimes you might be asked to show that two graphs are not isomorphic, right? And there's lots of different ways to do that, because you don't have to show that, you don't have to look at every possible bijection and show that none of them are isomorphisms, right? That would be a bit tedious. Sometimes there's a quick way to just, quickly show that some two graphs are not isomorphic, right? For example, if the two graphs have a different number of vertices, well, they can't be isomorphic, right? Because they can't be the same graph up to changing the names. So that's one way to rule out isomorphism, is just say, these graphs have a different number of vertices, they're not isomorphic. Another way to do it is to just say, okay, I count up the edges. If they have a different number of edges, they can't be isomorphic. Another kind of more subtle way of doing it, or more detailed way of kind of testing isomorphism, is to look at the degree sequence, right? What's the degree sequence? So the degree sequence is what you get by writing the degrees of the vertices in a sequence, okay? And we're going to do this generally in increasing order. So for example, if I took this graph, so it has a vertex of degree 1, which is here. It has 2 vertices of degree 2, 3 vertices of degree 3. And so its degree sequence is 1, 2, 2, 3, 3, 3. And if you think about it, it's pretty clear that two isomorphic graphs have to have the same degree sequence. Okay. Now, you have to be careful because this doesn't work in the other direction. If you have two graphs with the same degree sequence, they might not be isomorphic. Okay. So it only goes in one direction. But basically, if you can ever find like usually when you can find a property of one graph that the other graph doesn't have or something, then usually that will imply that they are not isomorphic. So let me kind of drive home this thing about degree sequence. So like I said, having the same degree sequence does not mean that the graphs are isomorphic. Here's an example. So here I've got two graphs where they've got the same number of vertices, 6 vertices, same number of edges, 7 edges, same degree sequence, right? The degree sequence is 2, 2, 2, 2, 3, 3. because there's 2 vertices of degree 3 and 4 of degree 2. But they're not isomorphic, right? Because if I look at, I mean, you can kind of tell by looking at it, they're not the same graph. Because, for example, this one has a triangle, like this one has, contains, so here's one way to show that things are not isomorphic, right? This contains this thing as a subgraph, but that one, does not. Okay. There's various different ways to argue this, but I think it's clear from the picture, these are not the same graph, right? Any questions about anything so far? Okay. Now, I've given you a million definitions. Let's actually prove something now. It's not the most exciting thing in the world, but it's something. It's actually very valuable though. So we're going to use this a whole bunch of times. So not only in the assignments and the tests, you have to remember this lemma, but we're actually going to apply this pretty soon in a kind of unexpected place. Maybe it's not unexpected, I'm not sure, but we'll see. So for every graph G, so the handshaking lemma says that if I add up over all vertices of G, the degree of G, or sorry, the degree of V in G, then that equals 2 times the number of edges in G. Okay, so how do we prove that? And it's actually, so the sentence that's already pre-written on the slide is almost the whole proof. But yeah, so if I take an edge, take any edge in the graph, let's call it E, let's say take E equal, some edge E, which is UV. So you can think about how much does this edge E contribute to both sides of this equality, right? So the thing is, like, imagine what I mean by this, I guess, is if I deleted E, how much would each side of this inequality go down, or this equality go down? So if I deleted E, the degree of V would go down by 1, right? So if we deleted E, then the degree of V would change. So it would become the degree minus 1, right? And similarly, this would go to degree of, so the degree of U would go to the degree of U minus 1. And nothing else will change. And also, like the number of edges, E of G would become E of G minus 1, right? So the arrows I'm drawing here just means would become. I just don't have enough space in the slide to write all the words. But yeah, so the way that both equations would change by 2, so both sides would decrease by 2. Formally, I guess I could say we're kind of done by induction or something, right? But I mean, really, we don't actually need induction here. I mean, in fact, you don't even really need all of this calculation here. This is just kind of trying to explain it. I mean, really, each edge, like if I consider how many times each edge is counted by each side of the equality, I can just say, like, it's twice, right? I mean, I guess all of this stuff below is kind of valuable for that, right? Because the point is that the presence of the edge E increases the degree of both of its endpoints by 1, so that adds 2 to the left side, and it increases the number of edges by 1, so that adds 2 to the right side. And so each edge is counted twice on both sides. So this is a kind of combinatorial proof that these two things are equal, right? Because both sides of the equality count each edge twice. So they count the same thing. Okay, so this is not how I would formally write the proof properly. This is kind of, there's not a lot of room on the slide, but this hopefully gives you the ideas. So here's a poll now related to this handshaking lemma and, well, related to everything we've done so far. Does there exist a graph with degree sequence 3, 3, 4, 5, 5, 6, 6, 7? Remember, the degree sequence is a sequence that has all of the degrees of all of the vertices, right? So, and remember, yeah, you have this handshaking lemma. I'm not sure, is it clear whether it's valuable here or not? Maybe it's not. I suppose this is a hard question to answer in some sense. Well, it's hard to answer if you don't know what the point is, because if the answer is yes, I mean, in an assignment or something, I would ask you to actually draw the graph, right? If the answer is yes, the only way to really prove that is to draw the graph, right? If the answer is no, then sometimes you can get away with an easy reason, okay? So, Okay, I'll leave this open for a second and just kind of discuss it a little bit. But yeah, I think there's a bit of a mix in the results. But so the point is here, I mean, this is using what we just learned, the handshaking lemma, right? Because if suppose the graph exists, suppose such a graph exists, so what if I take the sum of the degrees of vertices in that graph? Okay, now I have to add up numbers. 6, 10, 15, 20, 26, 32, 39, right? That would be equal to 39. But that's problematic, isn't it? Because by the handshaking lemma, the sum of the degrees is twice the number of edges, right? So this equality is by the handshaking lemma. But then that would mean that the number of edges is like 19 and a half. Like it's 39 divided by 2. That's impossible, right? There's no such thing as a half edge. So actually, the answer is no, there doesn't exist any graph with this degree sequence. Because, so the key thing here is that because of the handshaking lemma, if I add up the degrees of vertices of a graph, it has to add up to an even number. Because specifically it adds up to 2 times the number of edges, okay? But in particular, that's an even number. Okay, so that's a nice practice, and so you should get familiar with these sorts of questions. Also, this idea of handshaking and having an even, like the sum of the degrees being even is going to be applied. I think it's in the next class on Thursday. Okay, another definition. So a walk in a graph is kind of what you might think it is. So a walk in a graph is basically what you get by starting at some vertex and then walking around to other vertices, where when you take a step, what you do is you go across an edge, right? So it's like, imagine this as a network. You start somewhere and you can walk around, and you can walk back, you can retrace your steps and go backwards. You can walk around in a loop. You can do whatever you want, basically. Formally, mathematically, a walk is a sequence of vertices. I didn't say vertices here, so I should also add that xi is in v of g for all I. But formally, a walk is a sequence of vertices x1 up to xk for some k at least 1, such that if I look at consecutive vertices, they are adjacent. So xi is adjacent to xi plus 1 for all I between 1 and k minus 1. So for example, in this graph, if I take y, r, s, r, t, q, y, that's a walk, right? Because I start at y, I go to r, I go to s, I go back to r, so you're allowed to go back and retrace your steps. I go over to t. This picture is really messy. I go over to q and go back to y, right? That's a walk because everything I did went along the edges. If I take p, q, t, y, r, s, v, that's not a walk, for example, because of this pair, right? You can't get from t to y in one step. There's no edge. So that's why it's not a walk. Now, we're sometimes interested in special types of walks. So remember I said a walk can basically do whatever it wants. It can retrace its steps, like it can go backwards where it came from. It can come back to the same vertex over and over. It can do whatever it wants. But sometimes we're interested in like a more restricted type of walk. So for example, a path is a walk that doesn't come back to the same vertex. So for example, if I took y, r, t, q, y, well, that's not a walk, and we don't even really need to look at the picture to see why. It's not a walk, or sorry, it is a walk, I think, y, r, t, q, y, yes, it's a walk. It's not a path because it starts at y and it ends at y, right? So, so the vertices are not distinct. If I take q, y, r, s, that is a walk. Q, y, r, s is a walk. And so I'm also talking about, so we also sometimes want to talk about the length of a walk, or sorry, I keep saying walk, I mean a path. So yeah, what I said on the slide here is correct. What I keep saying is, I mean, it is a walk. Q, y, r, s is a walk, but it's also a path, right? Because it doesn't have any repeated vertices. And the length of a path is like the number of jumps, like the number of edges the number of steps you do in the walk, so, or path. So the length of a walk is also the number of steps. So if I take Q, Y, R, S, that has 4 vertices, but the length is 3, because it's like I took 1 step here from Q to Y, a second step from Y to R, and third from R to S. So if I ever talk about the length of a path, I mean the number of vertices minus 1. Okay. Any questions about that? Okay. So yet another definition. So a cycle is a path where the first vertex is adjacent to the last vertex. So for example, it's so here if I take x1, x2 up to xk, or sorry, if I take a, b, c, d, e, f, g, so you can see that this is a path, a, b, c, d, e, f, g, and it's a cycle because there's an edge between a and g. So sort of, I mean, if I think of this as a path, I kind of don't color this last edge because I don't consider it part of the path. But in a cycle, we kind of think of this last edge as being part of the cycle, right? So a cycle is literally a bunch of distinct vertices that form a cycle, like how you would think of it, like that there's edges that go from one to the other all the way around. Quickly check something. I think we're practically done what we wanted to do today. Oh, yes. So very important thing is to just get familiar with these definitions. Let me just check. Yeah, that's really, yeah, so getting familiar with these definitions is probably the most important thing. Maybe since I've got a bit of time, I will mention another definition. So yeah, so a graph is, again, it's a bunch of vertices, and you have lines that go between them, which are edges. And the edges were subsets, right? So they're undirected. Like there's no direction. You can think of an edge as being like a two-way street, right? You can walk across the edge in both directions. So a digraph, so another definition, a digraph or a directed graph is a pair. So it's very similar to a graph. So V, I'm going to call the edge set of a digraph. I'm not going to call them edges. I'm going to call them arcs, just for some distinction. So in a digraph, you have vertices and you have arcs. So where, again, V is a set and A is a subset of V cross V, meaning that it's a bunch of tuples. So it's so V cross V is just the set of all, let's say U, V, such that U and V are in V. It's just pairs of vertices, and we think of arcs as as being directed edges, kind of like a one-way street, whereas the edges of a graph are kind of two-way streets. Okay, so for example, so the way I draw digraphs is using arrows on the edges. So yeah, so if I take A, B, and C, this would be a digraph. So if I take, I can draw it like this. And note that you can also have edges that go the other way. And technically, you can also have edges that go from one vertex to itself. So if I let D be this digraph, then D is the digraph where the vertex set is ABC, and the arc set is AB. Okay, and again, I can write AB. In some sense, this can get confusing because we have digraphs and graphs. Maybe I'll just for now keep the notation like this. So you write the arcs like this. So writing AB means that that corresponds to this arc between A and B. So it goes from A to B. I've got BC, CB, and AA. So the correspondence is like this. So BC is the one that goes from B to C, right? I'm kind of just muddying this up, I guess. Maybe I'll use the highlighter. So CB is this one. And then, of course, AA is the arc that goes from A to itself.